So this is 125, CISSP, and the first thing I ought to do, I get various people contacting me. They don't understand what I mean when they say you need to turn in your topic today. So let me talk about that. We're here. Topic 1 due. All this means is you have to write a few words, like the title of your presentation you're going to give. You'll have to give a presentation in a few weeks and write a paper in a few weeks after that. And you can do them both on the same topic or different ones. But by today, you should go in Canvas and just upload some text in the topic, just to show that you've been thinking about it and chosen a topic of some kind. Any kind of security topic is fine. That's all this is. There are people apparently hunting around for like instructions and expecting this to be like a hands-on project or something. That's all it is. Choose a topic by today just to show that you're making some progress, and then within the next few weeks you should be thinking about your presentation. And the presentations are only 4 minutes long. Anyway, so let's talk about first bit of this very long chapter that will take us about 3 weeks to get through, security engineering. All right, so we're going to talk about security models, which is the material I've never seen anywhere except the CISSP about the BIBA model and Bell-LaPadula, which is what underlies, theoretically, all the security models we see in all the operating systems, and then things about hardware and virtualization and so on. So, the security models. Here's a summary of them, and the main thing, in order to remember these, the main ones with names on them are alphabetical. First came Bell, then came Biba, then came Clark-Wilson. That's how I remember them, and they also have a natural logical progression as you understand how they work. The Bell model was the simplest one that protects confidentiality, making secret secret. And that turned out to be not the perfect thing to do, so then came the Biba as the improvement on that, and the Clark-Wilson as the improvement on that. And we'll talk about all these other kinds as we go ahead. So here's the general idea. A lot of these talk about down and up. Down is less secret, up is more secret. So unclassified is down, top secret is up. So if you say no read up, they mean somebody whose clearance is confidential is not allowed to read stuff that is secret, because that would be reading up. All right, so that's the simple security property, no read up. This is the most obvious thing for the simplest kind of security. Obviously, the whole point of making things secret is so people who are not cleared with secret clearance are not allowed to see them. So no read up is the most simple, obvious security policy. That would seem to be the most important thing, and that's the Bell-LaPadula model. No read up is what it has. All right. Now, writing up would be okay. You could have a low-level analyst who reads an email or something and says, hey, this is important, and they pass it to their boss, and their boss moves that up to secret or top secret level. Now, that is understandable. Something that from a low level could be assigned a high level of clearance. Writing up is okay. That's not a violation of confidentiality. But no write down is also part of the model. So there's no read up and no write down for the Bell-LaPadula model, because you can't take top secret data and write it down. Now, the only way that could be done, of course, is to go through a formal process of declassifying it. So that top secret stuff is now considered only secret or unclassified. So that's the only way it could move down, is if it stops being top secret. So this all seems extremely obvious, extremely simple, and that's why it was the first formal security model. They said, well, this is what you mean by security, keeping the secrets secret. And that means no read up and no write down. And it seemed like that would be enough to make a secure system, but that turned out not to be true. All right, so people with top secret clearance can read anything lower. Read down is okay, but not read up. All right, so the problem with this model is it only provides confidentiality and nothing else. And this is when they did not yet understand that you need confidentiality, availability, and integrity. And it doesn't have that. All it gives you is confidentiality and nothing else. And it turns out that is not the only thing you actually want for security. All right, and something is beeping at me. Okay, anyway, all right. I'll take care of that later. All right, so there's a state machine model is another way to do it. Another way to formally define computer security, where you have a mathematical model and you have various states, possible interactions, like this person can read that, this person can write to that, and you make sure that the state of the system obeys your security policy, and you make sure that every possible state the system can reach still obeys your security model. That would be what it means to be secure. So the Bell LaPadula model was defined for the Department of Defense, and their first issue was confidentiality. No read up and no write down. This gives you confidentiality. The problem is it doesn't give you integrity. You could have a low clearance operative who submits false data, which goes up to high clearance levels, and that messes up your secrets. Even though they can't read the secrets, they can write up, and writing up could corrupt your secrets. So you haven't got integrity. And that's a problem. You have confidentiality, but you don't have integrity if these are your only rules, because an unauthorized person can alter data. All right, so another property people talk about is tranquility, where you don't change security labels while the system is running. It's another desirable property of systems. And here's another one called lattice-based, where you have various clearances and classifications of people, and subjects have a least upper bound and a greatest lower bound of access. So it's a different way of specifying things than just saying you're cleared for top secret, you're cleared for secret. So there's alpha, beta, gamma is the highest level of access. And you have this thing called the lattice, as people with the most privileges are up here and people with intermediate privileges are there. A sort of more complicated system. And I don't know much about it. And remember, like I said, the CISSP is a mile wide and an inch deep. You just need to know like the most important couple of facts about each of these things. But that's one of them. But the BIBA model, Bell, BIBA, and Clark Wilson are the main ones that I learned, and the main ones I think you need to know for the test. The others may come up a little. So the BIBA model is the opposite of the Bell model. So it appears to be insane. You don't let people read down. So people at high clearance levels cannot read low clearance level data. And you have no write up. So low level subjects cannot change high level data. So this protects integrity but not confidentiality. And this seems kind of nuts, but it occurred to me, this is essentially the Catholic Church. You have this top object called the Bible, and everybody can read it, but nobody can change it. It's a whole different system. You have integrity. Everybody can refer to this one master thing that can never be changed, so you can't deviate from your mission. But there are no secrets. It's just the opposite. Anyway, that's integrity without confidentiality. Anyway, so that's the game here. This is more for businesses than the military, and this is where you begin to get the clue, which is what we talked about earlier. In the modern world, you have availability, integrity, and confidentiality, and they all kind of oppose. So if you want the maximum integrity, you don't have confidentiality, and if you want the maximum confidentiality, you don't have integrity. So in the real world, you have to compromise between these goals. So then you get to the Clark Wilson, and the Clark Wilson is pretty much what everybody's really using now. This is what you get on like a Windows domain controller. You have subjects can access objects, and they have limitations, and you have transactions and separation of duties. These are primary concepts of this model. So well-formed transactions take untrusted input, which is called unconstrained data items, and you have a transaction procedure that will constrain it, which will take your untrusted data and fit it into your security policy and turn it into a constrained data item, which now is correctly stored and correctly marked with the right security properties, so it will stay within your security model. And then you have well-formed transactions, which move from one state of the system to another while maintaining your security policy. All right. And so it's not as simple as no read up or no write down. You have rules, which can be complicated. This person can do that. This person can do that. This object can go here but not there. And you can make that system as complicated as it needs to be to get the correct mixture of confidentiality and integrity and availability appropriate for your business. And separation of duties is another real important one. You don't let one person do something too crucial all by themselves. So one department collects money, another issues payments. Neither of them is authorized to initiate purchase orders. So this way, no one person can commit fraud. You'd have to have two people conspire to commit fraud. One person has to do the mathematical calculations to prepare the payment, and another person has to inspect it, audit it, and sign off on it. So two people both examine it before an important thing like sending money out happens. All right, let's take a look at a Kahoot. All right. All right. It'll be 3A whenever my thing moves. There we go. Yes. All right. Okay, there we are, 3A. Oh, yeah, that's right. Yeah, I didn't take my CISSP as seriously as some people. Turned out to be useful, though. I don't think I would have got these contracting jobs without my CISSP. So, but I'm not a management type wearing a suit. You know, I'm just a technical guy. But I do know how to talk to managers without insulting them a lot better than I used to. And that, I think, is an important CISSP skill. All right. Maybe we got everybody that's coming. Yeah, well, you have to. My sister told me this. You have to actually respect somebody if you want to influence them. If you have contempt for them, they won't cooperate with you. You have to get over being angry at them for being managers. And I did that. You know, I understand they're actually doing a job. It's important. It's different than my job, but I don't have to have contempt for them. It took me a while. Anyway, let's see how this goes. All right, which model gives you confidentiality but not integrity? All right, and that's it. The first one alphabetically, Bell. And someone says, are we doing 2 topics total in the semester? Yeah, in the whole semester, you do 2 papers and 2 presentations. So you can do that with just 2 topics. All right, so Bell's the first one, which is confidentiality. All right. Which model uses this alpha, beta, gamma stuff? All right, that's lattice. All right, which one has no read up? All right, and that's Bell, same one. No, that gives you confidentiality. People with low clearance can't read high clearance stuff. All right. All right, which one has no read down? All right, and that's BIBA, the second one, giving you integrity, but not confidentiality. All right, M will have to identify themselves better to get points, I think. Hadik, however, I can see who that is. And Mahmoud, I think that's enough information there. All right, good. So, information flow is another model where you limit how information flows, and this is a property of models that applies to both Bell and BIBA, where you may notice it didn't say something about how things are stored. It talks about information flow. You can't read up things at top secret clearance, can't flow down to people without top secret clearance, and so on. All right. The Chinese wall is another model where you try to avoid a conflict of interest. This is how one law firm could actually represent two clients on different sides of something in principle. It was originally designed for consultants in banks, where you somehow limit how information flows inside your company. So certain people are in this case and certain people are in that case, and they are not allowed to share data to try to avoid conflicts of interest within the same company. Non-interference is a very important and very difficult property to achieve of a security system. This is how you make sure that data at different security levels doesn't affect data at another security level. So, what is the other name of the Chinese wall? I don't know if there's another name. There might be another name for it, but that's the name I've always heard it called. Anyway, this is actually quite difficult. If your top secret data has some effect on, say, unclassified data, then that's a covert channel where someone can observe something unclassified and deduce something about top secret information. And that turns out to actually be very difficult to achieve in real hardware. For example, you might look at the power consumption or the radio emitted by a computer or something else. Another example is, I've heard this pizza orders in Washington, D.C. If we're going to have a major military move, they make all the staff stay late and they buy pizza. So you just call the pizza shop and ask how long it's going to take to get a pizza. You can deduce whether major military activity is underway in Washington. That sort of thing. An unclassified thing is affected by a classified activity, and that means some information is leaking out. Oh, Brewer-Nash. Oh, I think I might have heard that. Good. Thanks for the help, folks. Yeah, I think I have heard it called Brewer-Nash now that you mention it. All right. Then there's take-grant, where you can take privileges and grant privileges and create and remove things, and you have a complex model. So Alice has access to these secret documents. Alice can grant privileges to Carol, but Bob can take away Alice's privileges. So it's just another way to have a complex arrangement of different people having different powers to create the necessary security model for a business situation. And there's an access control matrix for user control provision. And this begins to look quite a bit like Microsoft Windows access control list. So you have users, and here's what they can do with this file, and here's whether they can create something. These persons can create things by executing the data creation. This person cannot create things. And then there's the Graham-Denning model, where you have 8 rules: transfer access, read object, create and destroy object, create and destroy subject. These are all just different ways to try to formalize, listing all the things you can do, and then rules of when you're allowed to do them and when you aren't allowed to do them, to try to create a realistic structure you can put in a computer that will maintain your security policy. The HRU model is the same kind of thing, but it only has 6 objects: create object and subject, destroy objects and subject, add a write in the matrix, or delete a write from the matrix. And so, from the Department of Defense directive in '88 comes the concept of modes of operation, which is defining how computer systems are going to handle information. So there's 4 modes: dedicated, system high, compartmented, and multi-level. The most secure is dedicated. And this is why, I don't know if it's still true, but there was a time when certain people in military had 7 computers on their desk, because you had to have a special computer just to handle one classification of information, and it had to be air-gapped from the next one, and the next one, and the next one. So you'd have completely separate systems to handle different levels of clearance. So you have a computer just for secret, a computer just for top secret, and so on. That seems like the most simply, obviously secure, and that's the game. And nobody's allowed to have access to that dedicated machine unless they have access approval and need to know. So they're cleared for that machine, for the data on that machine, and nobody else can touch it at all. That would seem like a simple way to protect confidentiality. But it's very expensive and complicated, of course. So system high is another one. The system contains objects of mixed labels, but all subjects must be cleared up to the highest object. So you don't expect the system to restrict information from users that aren't cleared. You simply don't let them in that locked room unless they're cleared. And then they can see all the data on that machine. Compartmented is where everybody touching it has the necessary clearance, but they don't have formal access approval, so they're placed into compartments. So you'll log in, and it will know what you're cleared to see, and you'll only see what you're cleared to see on that machine. But there is some data on that machine you're not cleared to see, and you are for the first time trusting some of the technical controls of the operating system to hide that data from you. So the previous 2 did not seem to trust the operating system at all. They just physically prevented you from accessing the machine unless you're cleared to see everything on that machine. But this one begins to use technical controls, and the last one is, of course, the cheapest and simplest and most common to set up. Well, maybe not simplest, but the most common, where you let many people log in, like what everybody does in the modern world. You all log into a web server like Yahoo, and Yahoo just keeps track of, you're only allowed to see your email and not other people's email. You have multiple people logging in with different clearances, and you have to have software to limit what they do, and that is called the reference monitor. The reference monitor figures out who you are and figures out what you're cleared to see and doesn't let you see the other stuff. So if a top secret person logs in, it figures out that you are cleared to see the top secret stuff, but if a secret person logs in, it says you're not cleared to see the top secret stuff. That's the multi-level system. One computer with multiple levels of people and multiple levels of information. All right. So you can evaluate these things, certify them, and accredit them. And it's compartmented, different from role-based access. It's a very similar concept, but I think compartmented talks about is aiming at the military, talking about need to know, usually based on area of specialization. Like you need to know about Russia, but you don't need to know about China. In a business world, you just use role-based access like manager and help desk and sales and so on, which amounts to a similar thing. It's just in a different environment. All right. So TCSEC is where it all started, the Orange Book from the Department of Defense in the 80s. And then after that came ITSEC and Common Criteria. Those are later improvements on TCSEC. Sure. So there's the picture of the glorious Orange Book determining what it takes to be a trusted computer system. And I learned a lot of these terms without being in the military because all the internals of Microsoft constantly refer to these terms because they carefully designed computer systems just to meet the requirements of this book so they could sell it to the government and the military. That's why you have a thing called a Trusted Platform Module in the hardware for a Windows machine so it can meet the requirements in this book to be a trusted platform. So anyway, this is part of NIST from the NSA, and it rates security on different levels. So D is like MS-DOS, or a floppy disk with FAT32, no control at all. If you have the floppy disk, you can read everything on it, no protection at all. C is discretionary protection. This is Microsoft Windows NT and a typical Windows home machine. You have an owner of the objects, an owner of the files, and the owner at their discretion can choose who to share the files with. So that's discretionary protection. Then you got mandatory protection, where you're getting more secure. Now you have labeled protection with these labels like secret and top secret, and some kind of structure to how those things are assigned. And then you have verified protection, where everything is audited and checked to make sure it's really working, and that's the highest level of security. So the Red Book was the network version of the same thing to try to define security levels for network systems. And then the ITsec was the European system to do the same thing, developed a little bit later, and it rated things in 3 areas: functionality, which is whether it works, and assurance, which is whether you can evaluate the security of it, effectiveness and correctness. So E0 was considered inadequate, and E6 is the highest level with a formal model. So there's a way they map more or less to each other. Like the A is up here at the F, B3 to E6, and E0 is the D. So it's slightly different and more complicated, but it amounts to the same general thing. And then, after both of those, came the International Common Criteria, intended to be this. Yeah, sure. Yeah, you got it. This is all military and spy stuff. That's where it all started. And all civilian security is just sort of a watered-down imitation of the military security, just like you'd think. So, now, in this one, you have the target of evaluation and the security target, which is a document defining your security requirements. And so you have a protection profile specifying what you've got, what level of security you're getting from something like a firewall, and an assurance level, which is the score of the system. And again, you can relate them, so as you see, it's quite simple. EAL, functionally tested, just means it works. Structurally tested, I think, means you've looked at the supply chain and things like that. Then methodically tested and checked, formally tested, and finally formally verified, designed, and tested means you've considered everything and recorded. You can prove that you considered all these risks, and so this is from the lowest security to the highest security. All right, let's take another Kahoot. 3B. All right. Yeah. I'll give it a few more seconds. All right. All right. So what security feature prevents covert channels? That's non-interference, so that whatever's going on at a high clearance does not affect anything at a low clearance, so the information is not leaking out. All right, so which mode enforces an air gap between each security level? That's dedicated. The system is dedicated to have one level of data, and people are not allowed to touch it unless they're cleared for that, and it's separated completely from the other systems. You have a dedicated system for each security level. You do not trust the operating system to limit things at all. You just limit it on the outside with physical access to the device. All right, which mode uses a reference monitor to control access? Not seeing the questions on your phone. Oh, that's not right. Are other people seeing the questions on your phone? Just the shapes. Perhaps I didn't turn on the option correctly. Okay, I must have forgot to turn it on this time. Thanks for telling me. I'll turn it on next time. Oh, for the last two Kahoots. Okay, thanks for telling me. There's an option to turn on, and somehow it must have got turned off. So I'll fix it for the next one. All right. Anyway, the reference monitor is used in the multi-level system where you actually have multiple people at different clearances using the same system, and they have to trust the operating system to keep track of who you are and limit it. Okay, thanks for telling me. I'll turn that on for the next one. The weakness of my amateur projection system is I don't really get to see what the students are seeing, so you got to tell me. All right. So what is the TC-SEC level for a typical home Windows laptop? Okay, that's C. This is like grades at school. A is the best, D is the worst, and that's level C, a modern Windows system. An MS-DOS system was more like D. Anyway, all right. All right, so what's the modern international security evaluation model? Yeah, common criteria is the new one. First there was TC-SEC, I think, then IT-SEC, and common criteria is the new one to be international across them both. All right. So let me record the winners, and I'll have to change that option next time. Reezy will have to probably tell me who they are. I know who that is. All right. All right. Well, let's go back to the slides. Okay, so here's some design concepts. Layering is one issue where you have these layers. You have the hardware, then you have the kernel of the operating system with device drivers that's close to the hardware, and then you have the operating system above that, and then applications above that. Anyway, this is the idea. Things are separated, and this turns out to be useful both for networking and for computer design to layer things so you can focus on just one level of things. Like you can write a word processor, and you don't have to worry much about the operating system or the device drivers. They can be separate, and one system can be updated at one level without necessarily changing the other ones. All right, so abstraction is a property where you hide unnecessary details from the user, and this is huge in computing. An average user just wants to see a web page or an email, and they don't want to see, a bunch of computer code or transistors or anything which is underlying that. They just see information at the level of abstraction that is appropriate for them. So security domains, this is where you group things together. So in kernel mode, you have low-level access to the hardware, but you then have user mode, which is a limited functionality of the system where you can only do a certain amount of activity and only a certain amount of harm. And now you have the property that your user mode application, like Microsoft Word, could crash, but it doesn't crash the whole computer and the other applications because you're not really getting to the really dangerous part of the computer. So this works with protection rings. The hardware supports 4 protection rings. Ring 0 is the kernel, and ring 3 is user, and there are 2 rings in between, but they're not used by any common modern operating system. So the only thing really used these days is ring 0 and ring 3. The kernel is in here, and if something goes wrong in the kernel, you get the blue screen of death and the whole system is dead, because that's the really important stuff. But if something crashes in the user land, you just crash one program, and the rest of the programs keep running. Now there is something else. All these models never really are perfect because people invent something new, and now we have hypervisor mode. If you were to run virtual machines on your operating system like Windows, the virtual machine, the hypervisor, technically runs below level 0 because it can actually have a kernel of the virtual machine that can operate in ring 0. So that's what these hardware-assisted virtualization technologies are that you'll see like Intel VT and AMD V. So an open system is a system where all the details of the computer chips and hardware are public. And this was the IBM PC. IBM made the PC. They published all the specs, so anybody could just buy them and build your own IBM-compatible PC. The alternative was Apple. The early Apple machines were completely secret. They would remove the serial numbers from the chips. It was considered a confidential proprietary secret how they work. And then they switched to Intel, a more open architecture, but now they've switched to the M1 with their own custom ARM chips, and I really don't know how open that is. I think they might be moving back to the closed model again, although somebody that knows more about Apple hardware than me could chime in and help. Anyway, so then we can talk about the hardware architecture. So the system unit is the computer case itself. If you think of an old desktop PC where it's not all in one box like a laptop, you have this case with the internal components, and then you have the monitor and keyboard plugged into it. There's a motherboard, which contains the processing unit, the RAM, and peripheral slots for add-ons like a network card in the older machines. And then you got the bus. The bus is the communication channel between components. So the CPU has got an arithmetic logic unit and a control unit, and it's sending data, and some of that data goes to the RAM or the hard disk, the display, the keyboard, and so on. And you have buses to move that data around, which are just a bunch of parallel wires mostly on the motherboard. And now we have North Bridge and South Bridge. The North Bridge is the high-speed bus to reach things that really need the data fast, like the video and the RAM, and the South Bridge is things that can be slower, like the keyboard and the mouse and the USB, where a fraction of a second of delay is not really going to matter. All right, so the CPU is the brains of the computer. The arithmetic logic unit does mathematical or logical operations, which are the same thing as far as the computer is concerned. And the control unit is what keeps track of which instruction you're doing, fetching instructions, and remembering where the next instruction is to move things to the ALU one at a time. So it fetches an instruction, it decodes it, it executes it, and then writes the result, and that's one clock cycle. And one instruction might take many clock cycles. Interrupts are things that are not done in order. So something happens, like a signal coming in from the hardware, like somebody has pressed, say, the power off button. It doesn't just kill the power for the processor, it sends an interrupt to the system saying, wait, an important thing has happened. So pay attention to this and service the interrupt before you resume your previous task. So the task is broken into threads. One process, like you launch like Microsoft Word, will be broken up into threads, and those threads can proceed independently. So if one thread is waiting for something slow, like user input, other parts of the program can continue forward in other threads. And that's the idea. So one huge problem in computing is you have a fast processor, but you have many slow devices, like the hard drive and the user typing on the keyboard and the network card. And you really don't want that fast processor to be just waiting for some slow thing to respond if you can avoid it. You'd like the things that can move forward to keep moving forward. So all modern systems are multitasking. They can run multiple programs at once, even though there may be only one CPU, although most people have maybe 4 cores on their CPUs these days. If you're running a bunch of programs at once, they're not really all moving at the same time. It's giving each one a few cycles, the next one a few cycles, alternating between them. But to us, it looks like they're all running at once. Now, you can do multiprocessing, where you have one task being done by multiple processors, and then you've got symmetric multiprocessing or asymmetric multiprocessing, whether the individual machines, individual processors are cooperating very closely or less closely. But anyway, that's what happens if you have multiprocessor CPUs, which most of us actually have these days. It says Intel architecture, but stolen from AMD for most of it. Well, yes, there's that. Yes, there are, of course, arguments all the time about the intellectual property. Yeah. But I guess now that Apple has moved to M1, they really own that. Or, I don't know, maybe they bought that from somebody. Now there's the M2 also, which I know nothing about. Anyway, so there's a Watchdog Timer, which tests to see if you need to reboot the system after something has crashed. And here's the issue that has gone back and forth. Intel uses CISSP, Complex Instruction Set Computer. There's something like 10,000 instructions, and it's a really boring list. You can move from register to register, move from register to memory, move from register to memory plus a constant, move from register plus memory plus a register address, and so on. You know, it's just many, many versions of the same instruction. So one philosophy is you should do that so you can carefully choose the one instruction which will most efficiently do what you're doing. But the alternative is ARM, which is the reduced instruction set, where you have a small number of instructions, and therefore it might take several instructions to do something. So if you want to add one number in memory to another number in memory in ARM, you have to first copy the first one to a register, then copy the second one to a register, then add the registers, then take the result and put it back in memory. So it's like 4 machine language instructions to accomplish that task, which you might be able to do with 1 or 2 instructions in Intel. And I say originally Mac was using reduced instruction set computers. Intel used complex instruction set, then Mac moved to the complex instruction set, and now they've moved away from it back to reduced with going back to ARM. For the last 5 years, I've been seeing articles saying everyone is going to go back to RISC and use ARM because it uses less power per instruction. And as everybody's moving to portable devices and so on, they're going to want the power efficiency of ARM. And that may happen, but it hasn't happened yet. A lot of people are still using Intel. So direct addressing and indirect addressing is here. Yeah, a lot of people have moved more towards ARM, but Windows doesn't even have an official ARM version yet. So, Windows people are still using Intel entirely. Oh, Intel used a RISC chip. Oh, I didn't know that. Never heard about it. Good. Anyway, so you can have an immediate value. If you add EAX8, then if your EAX register contains 1, you just add 8, and now it contains 9. So the 8 here is just an immediate value, just a number to be added to something. You can have a direct address where you add EAX to memory location 8. So now it'll take EAX, go to memory location 8 and find out whatever's there and add that into EAX. And then you can have indirect address where you add the memory pointed to by EAX to 8. So if this EAX has 12, you go find location 12 and get that number and add that. So anyway, this is immediate values, direct addresses, and indirect addresses. Then there's memory protection, which is, are there permissions in RAM? And on the hard drive, every file has an owner and it has a modification date and a lot of useful information. But on memory, that's not true so much. So they're all sharing one block of RAM, like you have 4 gigabytes of RAM. So can you protect one area of memory from another? Well, you can, but the protection is simpler and much less sophisticated than what happens on the hard drive. This is process isolation. So you have one process that's not allowed to interfere with another process. So each process runs with virtual memory addresses, and it can only access memory in the memory that's allocated to that process. And this is what the whole 127 course I'm teaching this semester is about. Exploit development is memory corruption, ways to overcome these defenses, ways to exploit some flaws in here. Anyway, so you have object encapsulation we'll talk about, and you have time multiplexing. Each process gets certain amounts of time, and the idea is the processes can't write to each other's memory and they can't interfere with each other's actions. So in real mode, this is the original old-fashioned system where there's no process isolation. Every process can write anywhere in RAM, and that's what happens during boot up. At a certain stage of boot up, it then switches to protected mode, where you have a limitation of what memory you can reach. Now, x64 processors don't use segmentation anymore, but they use something called memory paging to accomplish essentially the same thing. So virtual memory is the virtual address mapping between processes and memory. So this provides isolation, so each process, for example, all Windows processes, they all think they're loaded at 400,000 in hex. They're really wherever they need to be, but they think they're at 400,000. They work with a virtual address. Another thing you can do is you can allow your machine to run more running processes than you can support with your actual physical memory with paging. So if you open a browser, open Microsoft Word, open a game, open Photoshop, and you need more memory than you have, instead of just popping a box and saying you're out of memory, you need to buy a bigger computer, it will just take blocks of memory from RAM and put them in a temporary file on the hard disk. So you can still open a new program and use it. Now what will happen is when you try to go back to the older program, it will slow down and grind away as it reloads that memory from disk. So you'll pay with time eventually, but you can run more processes than you can actually support all at the same time in RAM. And so that's called a page fault. If you try to open the previous tab and that memory is no longer in RAM, that's called a page fault, and it swaps that page into RAM so you can run it. The BIOS is on a hardware chip. This is the code that's used to boot up the machine. It can be modified, powered by a small battery, but the only thing that's in there is typically what type of hard drive you have, what other accessories are on your machine, so it can just boot up and find the hardware. So it runs a power on self-test to see if you have a storage device, a keyboard, a monitor, and so on, and then it boots up. Worm storage is things you can write once, but read many times, so you have integrity. This is the point of CDRs and DVRs and ROM chips. They are burned once, and then you can use them, but you can't change them, so you know that nobody's been modifying what's on there. The Trusted Platform module I mentioned before is a hardware device added to Windows machines around the time Microsoft brought out Windows Vista in order to meet military requirements, so it would be a trusted platform for military data. So it's a cryptographic coprocessor, and therefore you can have cryptographic keys that are available to the TPM that are not available to the processor. So you can have secret keys in there, and no malware in the processor can steal them because they're not anywhere in the address space of the processor. There's the same thing in your iPhone called a secure element, which is what holds the root of the key used to encrypt credit card numbers, which is why Apple Pay is very secure, more secure than using a physical credit card. So it's a very good idea. You have, and this can be used also to verify the integrity of the operating system during boot up and end rootkits. So that if anything tries to modify the kernel of the operating system, it will detect that. And it's also used to encrypt the hard disk with Microsoft's hard disk encryption. Data execution prevention is another thing Microsoft brought in around the time of Vista, where you can mark areas of RAM non-executable, which prevents buffer overflow attacks, and we'll spend quite a lot of time dealing with this in the exploit development course. So even if you find a program error that lets you inject data where you shouldn't be able to, will find that you can't run it, and that will stop the whole generation of malware. Address-based layout randomization is another defense. It used to just be that every time you launch a program, it finds the first available memory and puts it there. And that means you could pretty much predict what area of RAM something was running in. So this randomizes it. You load the operating system, it randomly chooses RAM, you load your antivirus, you load your other processes. They get randomly relocated in RAM after each reboot, so an attacker who finds a way to inject code doesn't know where that code is. It could be anywhere in memory. So that slowed down a whole other generation of attacks. DEP and ASLR together ended the original type buffer overflow attack, which was all the rage in Windows machines, Windows XP and earlier. All right, let's take a look at another Kahoot, and I'll see if I can find that setting, 3C. There is a setting to project it on your phones, and let me find it. I had it set before, but apparently it did not persist as well as it should. Game options. Ah, there it is. That was turned off. There, this should be more like the way it should be. All right. And it should be randomizing the order of the answers, too. All right, good. Well, thanks for telling me. And if anything's wrong, you please tell me, because I don't have an easy way to tell. Yeah, that's right. S0. That's what it was. You only saw the colored boxes. That's the default. Projecting the questions is better for this environment where I'm using a delayed twitch. But it's not the default. So apparently I don't have it turned on for all my Kahoots yet. All right, I think we got everybody. All right, so what ring does user mode use? That's 3. Tariq, you can join the Kahoot, but I think you're annoying people putting answers in the chat. Anyway. All right, so users can't handle the truth, so the computer lies to you. What is the term for that? All right, that's abstraction. See things only at a certain level. You can just join by going to kahoot.it if you like. Anyway, all right. So, all right. So what's the communication channel between components? All right, that's the bus. Good. All right, so if I launch Microsoft Word, what does that do? Yeah, that's a process which will contain one or more threads. All right. All right, and where's the cryptographic coprocessor? That's it, the Trusted Platform Module. A lot of people are getting bent out of shape because Windows 11 requires the new GPM2. Anyway. All right, that's Hadik. And good, another two-time winner. And Mohammed, they're all two-time winners. Good. All right. Well, let's take a 10-minute break. It's about 7 after. I'll come back at 7:15, and we can do one more section for today. So I'll be back in, I guess, 8 minutes.